Welcome to one of our last lessons in our factoring unit here. Now that we've learned how to factor in a variety of different ways, now we're going to start to look at some of those special cases where we could maybe take some shortcuts or where there's a quick way to get to a solution. So today we're going to focus on something called difference of squares. So if you remember back to an earlier lesson, we had problems like a plus b times a minus b. So it's the same first term, the same last term, the only difference is switching the signs in the middle. And if you remember what happened, we would do a times a is a squared, we do b times b is b squared, but then those middle terms, a times negative b is negative ab, b times a is positive ab, those two middle terms added to 0, and we are just left with a squared minus b squared, okay? Because it was the same values, just a different sign, we only ended up with that first and last term. Those middle terms turned to 0 and dropped out of the problem. So we're going to tackle that same idea but in reverse. So now we're going to have some perfect square binomials and we want to factor it back into the original two pieces. So the first thing we always check is, are each of our terms perfect squares? So something times itself. Well, m squared is m times m. 10 or 100 is 10 times 10. So I know it's going to work. Then all we do is set it up. My first term is going to be my m. My last term is going to be my 10. But because I want that middle term to drop out, I need one to be plus and one to be minus. I mean, it doesn't matter which one, but I want to always have one of those drop out for me. Or sorry, I always want to have one positive and one negative for me. All right, next one. 25 is 5 times 5, so that's a perfect square. 16n squared. Well, 16 is 4 times 4. N squared is n times n, so that one works as well. So I get 4n plus 5 and 4n minus 5. I just want those different signs so that middle term turns to 0. Next one, 36x squared. Well, that's 6x times 6x. 100y squared is 10y times 10y. So that is a perfect square. So we just separate each of the two pieces and switch the signs. So I have 6x minus 10y and 6x plus 10y. Once we know what those two pieces are, and it's always got to be that subtraction in the middle, because it was a negative times a positive for that last term, we can go ahead and factor it out. All right. So similar to some of our other problems, sometimes we might not see numbers that are perfect squares, but we always look to see, can I factor something out of the problem first? Well, 50a squared minus 72. Those are not perfect squares, but I can factor out a greatest common factor of 2. So I can factor out a 2, and I get 25a squared minus 36. Now, that is a perfect square. 25a squared is really 5a times 5a. 36 is really 6 times 6. I want different signs, so one's plus and one's minus, and then that 2 that I factored out just hangs out front. So sometimes we got to do a little bit of work first before we can finish using our difference of squares. All right, so I'm going to do these rapid fire. This one's very similar to that last one. I can factor out a 2. So I get 36p squared minus 25. 36p squared is 6p times 6p. 25 is 5 times 5. And I switch my signs. And my 2 hangs out front. Here I can factor out a 2. So I get negative 1 plus x squared. I'm going to rewrite it as x squared minus 1, because that's usually how I want to look for it. I want that squared term up front, and then I want that subtracting in between the two of them. Okay? I could have also factored out a negative 2 from each of them if I wanted to switch their signs. So my 2 hangs out front. X squared is just x times x. 1 is just 1 times 1. And then I want opposite signs, a plus and a minus. All right. So let's do number 7 here real quick. I'm going to just do a handful of them. 121m squared, well, that's 11m times 11m. 144p squared is 12 times p and 12 times p. And because I want that middle term to drop out, I want 1 to be plus and 1 to be minus. All right, let's do 24 here real quick. So, or sorry, 9. 24a squared minus 54b squared. Well, neither one of those are perfect squares, but they do have a common factor of 6. So I can divide a 6 out of each of them, and I get 4a squared minus 9b squared. Now, 4 and 9 are both perfect squares. So 4a squared would be 2a times 2a. 9b squared would be 3b times 3b, and then I just switch the signs. It doesn't matter which one you list first, the plus or the minus. All right, so now we're going to put this with the next part. So similar to the previous lessons on factoring, once we learn how to pull it into its separate pieces, we're going to use our zero product property, meaning we're going to set each of those pieces equal to 0, and then solve them to find the actual solutions, the roots to this problem. So 81x squared equals 49. Again, get all your terms on one side. So 81x squared minus 49 is equal to 0, because I subtracted 49 from both sides. Now I factor my difference of squares. 81x squared is 9x times 9x. 49 is 7 times 7. And then I want 1 plus and 1 minus. Now I set each one equal to 0. 9x plus 7 is equal to 0. So x is equal to negative 7/9. I would subtract 7 from both sides and then divide by 9. 9x minus 7 is equal to 0. So x is equal to positive 7/9. We should get the same answer, just different signs, since we're working with the same numbers as we solve it. So number 2, again, get everything on the same side. So 36n squared minus 1 is equal to 0. 36n squared minus 1. 36n squared is 6n times 6n. 1 is 1 times 1. And I need 1 plus and 1 minus, and it's still equal to 0. Set each one equal to 0. So for this one, I'm going to add 1 to both sides and then divide by 6. Now we get n is equal to 1/6. Over here, I'm going to subtract 1 from both sides and then divide by 6. So n is equal to negative 1/6. And you can absolutely show all that work if we need to for each of those problems. All right, so now I'm going to jump down to number 4. So I have 49 hundredths minus x squared. So this one's going to feel a little weird, but we can totally handle this one. Just think of perfect squares. So 49 over 100. Well, 49 is 7 times 7. 100 is 10 times 10. So 7/10 times 7/10. X squared is just x times x. And I want 1 plus and 1 minus. And it's equal to 0. So 7/10 plus x is equal to 0. So x is equal to negative 7/10, because I'd have to subtract that 7/10 over. 7/10 minus x is equal to 0. Well, that means 7/10 is equal to x, because I could add the x to both sides. So I get a positive 7/10 and a negative 7/10. So let's do number 6. 27h to the third and 48h. Well, first things first, let's get them both on the same side. Okay, neither of those are perfect squares, so let's see what we can divide out of both of them. Well, 27 and 48 can each be divided by 3, and I can take an h out of each of them. So I can factor an h and a 3. So I get 9h squared minus 16 is equal to 0. So my 3h hangs out. 9h squared is 3h times 3h. 16 is 4 times 4, and then I want 1 plus and 1 minus. Now I go ahead and solve them, but I should do 3 of them because I have 3 parts. 3h is equal to 0, so h is equal to 0. 3h plus 4 is equal to 0, so h is equal to negative 4/3. 3h minus 4 is equal to 0, so h is equal to positive 4/3. So in this one, I ended up with 3 solutions. All right, let's do one more, number 8. So t squared is t times t. 64 over 121. Well, 64 is 8 times 8. 121 is 11 times 11. And then I want 1 plus and 1 minus, and it's still equal to 0. T plus 8 elevenths equals 0, so t is equal to negative 8 elevenths. Oh, not tenths, elevenths. T minus 8 elevenths is equal to 0, so t is equal to positive 8 elevenths. And those are my 2 solutions, my 2 roots to this.